Hello guys, and welcome to today's video. So we are going to look at an example of state space analysis. So this is an exam question. We are going to try to derive the state space equation of the electrical system shown in the figure below. So we want to derive the state space equation of this electrical system that is shown in the figure below. So solution. So how do we go about this? First of all, we need to identify, or let's analyze the system. So we have a current source. So this is perhaps our instantaneous current supply. And you can see that this current travels away from this source. And at this particular node A, it splits into IC and it splits into what? IL. So our I of T is splitting into IC and what? Into what? IL. So the IC charges the capacitor and produces what we call our capacitor voltage V sub C, and of course this IL goes across through an inductor with inductance L. Okay, eventually this IL is what is still going to flow through this particular resistor because we can't see any break in the branch. So you have IL. So this is our system. Now it is important that the two things that we are going to be taking as our energy elements will represent the state of our system. Now, when you're giving this kind of system and you're not really giving a specific definition as to what to take as the states of your system, okay, the state variables of your system, so you should choose the energy storage elements. So I'm going to be focusing on the capacitance and the inductance. Now, under capacitance, we are really interested in the capacitor voltage, that's the VC. Okay, so the capacitor voltage is one possible state, and under inductance we are very interested in the inductor current, which is what? IL. So we are going to use this particular two terms as our state variables. So that's the first declaration. So we select our state variables to be IL and VC. That's the inductor current and the capacitor voltage. So we're now going to derive equations from this system that will help us to derive the state of our system. Remember, to derive the state of this system, since we have selected our state variables as IL and VC, so we need to form our IL dots and our VC dots, okay, to be some particular matrix which we don't know what this matrix is going to contain, okay, but we just know that here will be IL and here will be what? VC, then plus any inputs. Okay, so this is how to get the state space representation of our system. So for two states, you're going to have a two-dimensional state matrix, okay, a 2x2 state matrix. So the state matrix is one of the most important things that we want to discover when we are getting the states. So how do we populate this particular matrix over here? So let's not be afraid. So we have the first equation. The first equation is that our current source I of t splits into what? IC and IL, okay, at node A. So you can see that at node A over here, this current source I of t, which is the input current or the input, have decided to split. Part of it goes to the capacitor to charge the capacitor arm, part goes into the inductor windings. So I of t from the current law, that's Kirchhoff's current law, it's gonna split into what? The two parts, okay, that's the algebraic sum of current entering or leaving a node is 0, or the sum of current entering a node is equal to the sum of currents leaving. So IT is entering this node and IC and IL are leaving, so you have IC plus IL. Okay, that is what is happening at this particular point. So we have the first equation Now, the second equation, you will agree with me that this is a point of potential. I can decide to measure my potential. I can measure my potential from this point to this point. So the potential difference from this point to this point is VC. That's the voltage across the capacitor. And you can see that since this capacitor is an energy storage element, the potential difference is going to be the sum of the voltage here and the voltage here, according to Thevenin's voltage law, or Kirchhoff's voltage law. Sorry, that's the algebraic sum of potentials in a loop is zero. In other words, just like energy is conserved in principle of conservation of energy, okay, the potential energy supplied, that's in terms of voltage, this VC will distribute into this VL and this VR. So another equation you could get from this system is VC is equal to voltage across the inductor plus voltage across the resistor. So this is a possible equation that we can get. Okay, so the potential across this point is the sum of the potential here and the potential here. Is that okay? So we write it like that in our equation 2. We can write our VC, that's voltage across the capacitance, is equal to VL plus VR. Is that okay? So this is another equation 2. Now, the final equation that we're going to work with is VC is equal to the voltage across the capacitance, okay, which is the point that we're interested in. The voltage across the capacitance is going to be, of course, for any capacitance given, you have 1 over C integral of IC dt. So this is equation 3. So this is the formula for calculating the voltage across a capacitor when you're given the capacitor current and the capacitance. You can calculate it like this. So these are the 3 equations that we're going to use to populate this state matrix that we have over here. Is that okay? So let's move on. Now, coming to equation 2, you have that VC is equal to what? VL plus VR. So you need to recall that VL is the same thing as what? L di L dt. Is that okay? L di L dt. So the IL meaning what? The current that flows across, flows through the windings of the inductor. Okay, so that is the formula for calculating the potential energy, the voltage in an inductor. While the voltage in a resistor by Ohm's law is simply IR. So it's still the inductor current that is going to pass through the resistor. So you now have your ILR. So if I replace this equation, you will discover that my VC will now transform into what? Your VL, which is what? L d IL over what? dt. Okay, then you now have what? Plus VR, which is what? ILR. Is that okay? So what can we see from this particular equation? Remember that one of the things we want to get is what? IL dot. So let me write it like this. IL dot. I'm going to write it like this. Let me just write it like this. And we're going to use capital V. So IL is the voltage across, is the current that is flowing through the inductor, and VC is the capacitor voltage. Now IL dot is the derivative of that current, Of course, you know every state, the state representation of a system. Once we obtain, let's say, 2 states, x1, x2, okay, then we'll now have our state matrix, which is A11, A12, A21, A22. Then it will be equal to x1 dots, x2 dots, okay, then plus inputs. So this is like the general form of having your state matrix. You need to obtain your states and their derivatives. So obtaining your state and their derivative is what will help you to populate the fields of this matrix. So it means that since I have identified my state as the current and the voltage, the inductor current and the capacitor voltage, I need to find the derivative, okay, of my state. And from this particular equation over here, you can decide to make the derivative of the current, okay, your subject of the formula. So you can have L d IL over dt will be equal to minus IL R plus VC. Is that okay? So you can divide through by L, so the IL over dt will be minus R over L. You now have your IL, and you now have your what? Plus VC. So your derivative of current, that's your I dots, okay, IL dots, is expressed in terms of your two states. That is your IL, your current flowing through the inductor, and your second state, which is the capacitance voltage. So you can call this equation, what equation did we stop? Equation 3. So you can call this equation 4. Is that okay? So we're going to make reference to it later. Then if we want to get the derivative of the capacitor voltage, we can actually make reference to this equation over here. So let's start from equation 3. So from equation 3, we are given that VC is 1 over C integral of IC dt. Now, if you differentiate both sides, you're going to have dvc over dt is equal to 1 over c and I of c. Okay, so you also have to recall, okay, from equation 1. So recall that our I of t, our input current, is equal to IC plus what? IL. In other words, if you decide to make IC the subject of the formula, you get that IC is the same thing as you having your minus IL then plus I of t, which is the input current. So IC is negative IL plus I of c. So plugging this into this equation, your dvc all over dt, which you want to find the derivative of the second state, is 1 over c. And you now have your I of t IC, which is minus IL then plus I of t. So if you simplify, dvc by dt is going to be negative 1 over c IL, then you now have plus what? 1 over c I of t. So you can call this equation 4. So let's put equation 3 and equation 4 together. So we obtained from equation 3, we obtained that our dIL dt is equal to, what we got was minus R over L. Minus R over L, we now have IL plus, okay, I think I made a mistake. Thank you for that observation. There's supposed to be a 1 over L here, 1 over L. So thank you for that. You know, when you divide through by L, dividing through by L, the 1 over L will also come to this place. So thank you for that. So this is plus 1 over L VC. So this is equation 3, and equation 4 we got dVC, okay, by dt is equal to, derivative is minus 1 all over c, now have IL plus 1 over c I of t. Is that okay? So I'm going to copy this to, I'm going to work on another section of our page. Okay, so this is what we obtained previously. Now we want to now wrap it up into our state matrix. So this is what we're going to get. We're going to get if you convert this to the matrix form, you're going to get dIL over dt, follow me, and you now have dVC all over dt in matrix form is equal to, so let's find our coefficients matrix. Coefficients matrix is the matrix comprising of the coefficients of the states. So we have our states as IL and VC in this order. Okay, then we'll not have any inputs. So you can see that from this first equation, the coefficient of IL is minus Sorry about that. The coefficient of IL is minus R over L. Minus R over L. Okay, now the coefficient of VC is 1 over L. There is no input term. So if at all there is an input term, the input term should be I of t. So in the first equation, there is no coefficient of I of t, so you can call it 0. Is that okay? Now, going to the second equation, you have your I of c as the 1 over c as the coefficient of IL. So that's, sorry, minus 1 over c as the coefficient of IL. Then the coefficient of VC is 0 in this case because it does not exist in this equation, so you can call it 0. But the coefficient of your input signal in this second equation is 1 over c, so you can put it here as 1 over c. So with this, you have been able to obtain the state space representation of the system that is given below. So you can actually call it your capital IL dot, your VC dot, okay, is equal to negative R over L minus 1 over c. You now have 1 over L 0. You have your capital IL, your VC, plus you can have 0. Some people like putting their I of t divided by c here, okay, or you could just put it as 1 over c, and you can put it as I of t. They're still the same thing. So this is the state space representation of the system, where IL dot is equal to di dt, the IL dt, and VC dot is equal to the VC dt. Okay, capital IL is your this, and your capital VC, okay, is your VC. So this is the state representation of your system. So I hope you understood it, and yeah, so this is about this one. So we're going to see state space representation of a mass spring system in the next problem. So stay tuned. It's another exam question and you want to know how to solve. All right, bye.